Hey guys, this is Arsh from Don't Blink. If you haven't checked out our hardware explanation video for Ultimate Goal, I would suggest you do that because that has some references to our robot right here. But this video, we're going to go through some of the software aspects, especially those that integrate with some of the hardware subsystems that we have on our robot, and also things that we didn't have enough time to do really well, but just things that would have helped us in the Ultimate Goal season that could be beneficial for future seasons. So we're going to go through things like that. So the first thing a lot of teams do is odometry. So if I just lift this robot onto its side really quick. So you can see our robot has 3 odometry pods. And something that we learned this season is that the metal odometry pods are way more accurate than something that's 3D printed. And this was through our personal testing because we use both 3D printed odometry pods as well as these metal ones. So these odometry pods are designed by team 18219 Primitive Data. So they basically have an open source odometry design known as Open Odometry. And we found that their design was really nice because it was really lessened the width and it provided enough stability to have a really robust odometry pod. Like there's like little to no give in like any direction. Like I physically cannot move any of these, and they have stuff like springing guides, wiring guides, all the things that you really need to get started with odometry. So this was our team's first year doing odometry. We haven't really done anything custom with software before the season, but since the season started, we experimented with things like Open Odometry and Roadrunner. So a lot of teams this year, they chose a variety of ways to do things like the autonomous pathing and localization for teleup even. And the three most common ways that we found were Pure Pursuit, Roadrunner, and then just using the encoders in other custom methods. So for our team, we found that Roadrunner was the best to work with because it was really easy to work with, but also it provided enough accuracy for us during the autonomous period, and that the integrated classes that Roadrunner provides is easy to work with, but they're really good as well. So for teams especially that are starting out, using Roadrunner, like that are starting out with odometry or localization, I would suggest that using Roadrunner would be the best option because something like Pure Pursuit can get a bit more complicated as there are not like any open classes that you can just copy and use, and that Roadrunner has a lot of integrated features that Pure Pursuit might not have, making it a little more user-friendly. And I haven't really seen much difference except for speed. It's just that Pure Pursuit is faster because unless you motion profile it, it just goes to the point as fast as possible. But using Roadrunner's localization was also super accurate because they use pose exponential map, and that's helped us maintain a really good accuracy on the field. So now going to some of the hacks we have with odometry. So our friend and mentor Hinopede. So one of the things he suggested is using the IMU if it's accurate enough. So our IMUs thankfully are pretty accurate. I know a lot of teams have problems with that. So something I would suggest is you don't have to use RevHub's IMU. You can use custom IMUs found that are legal for FTC. And one of the cool things that we learned from other teams is you can actually use the T265's IMU, which is Intel's RealSense camera. If you use their IMU is really accurate, even if their actual pose estimation is not. So if you use their IMU instead of your 3-wheel odometry setting or your RevHub's IMU, that can actually lead to some more accuracy. So anyway, his suggestion was instead of using 2-wheel plus IMU or doing something weird with that, you can actually use 3-wheel plus IMU to correct for a lot of errors that you have in your software. So one of the main things is caching out the odometry heading. So every 500 milliseconds, we call the RevHub's IMU. This way, we don't have really bad I2C calls since we're calling it every a loop. Instead, we're calling at an interval, and this helps us maintain a good heading because the RevHub's IMU can correct for that. And the other thing is also caching out error when we're at 0 heading. So what we found was our IMU is really accurate at 0 heading. So if the IMU ever reads 0, we just cache out our heading and set it to 0. And it just makes it much more accurate over the play. I think at the end of the season, our heading drift was definitely under half a degree over the match. We more so had problems with things like our strafe distance, but that was also mitigated. So using tips like this for localization really, really helps because you can customize and automate a lot of the features on your robot. The thing we want to do next season, which we didn't get to this season, is PNP localization using vision, or just tracking targets to reset your odometry pose, so that you don't have to drive to a specific target and reset it. You can just automatically do it whenever you want to using vision. Another thing is making a lot of assists for your drivers. That's really important as well. If I flip the robot back up here, we obviously have a turret for this season, so making this auto aim to the goal is really important. So we use odometry for this. We tested out vision. Vision was a bit laggy for us, but we found that like our odometry readings were sufficient enough that we could just use that. Something that's really cool about our turret is we use feed forward. A lot of teams on a lot of mechanisms just tend to use PID, but feed forward really makes the actual motion following, just like the way the system interacts, it's a lot more smoother, and it can get more accurate depending on how you set it up, because you can add profiles to the feed forward how you want to, and you can make it, make the whole system of getting to a target more accurate with PID. So the way our feed forward works for the turret in very layman's terms is that the turret actually offsets itself based on our robot's angular velocity. So if our robot turns really fast this way, our turret will turn really fast this way. And if our robot moves really fast in a direction, it'll account for that in the feed forward. So if we actually turn off the PID, our turret is still pretty accurate. Again, our mentor helped us a little bit with this. And on top of that, we just have a PID system. So we use PID to turn to a target position. And what's really cool is that we use both P, I, and D. So again, just to reiterate, so P is used for getting to the target position based on coefficient, like proportional error. And then the derivative is used to smooth out the velocity, and then integral helps with like really, really small, tolerances where a PD controller won't really be sufficient. And just tuning that a little bit and making it smooth really helps with any system that you want to track. We also use odometry to adjust the flaps position on our shooter. So based on the XY distance, so like the closest distance to the goal, our flap adjusts to the best position possible. And a tip that we picked up from 6165 was to make it so that the rings are a little bit, the term that was used for ultimate goal is roofing. So it hits the highest point possible for the high goal. So that way, if you have a drop in your shots, you can actually still be fine because you're hitting the first shot all the way as high as possible. So that's how we set up the flap. Another thing that's also helpful is reading your shooter's velocity. So we have a velocity PID on this, but you can also add conditions that you don't shoot when you're under a certain threshold. And Delta V was the one who told us about this, and then through our own testing, we also got things where we wanted to shoot and where we didn't want to shoot. Other things is you could add the distance sensor to read the number of rings. We didn't really need that since we had an open like view design, so we would just be able to see it if something got stuck. And if we ever had more than 3, we just turned the turret to 0 and shot out. What's really cool is on our old robot, our hopper actually automatically ejected the 4th ring, much like Black Forest Robotics. But with this one, we couldn't really do that. One really crazy idea we had was removing this top plate here and making the top plate actuated. So if a 4th ring ever came in, the top plate would just go down like this and the ring would just fly over. But we didn't really see a need for that. It was getting late for MTI anyway, so we just left it out. Other software automations, for autonomous, we use Roadrunner and just combine all these systems. I think what's important is the way we set up our code. We try to make everything really adjustable in our code. So if we ever make changes to our robot, it should just be a 1 value change in our code. And I know a lot of teams use like command-based or finite state machines and things like that. With our autonomous programs, we just use the trajectory sequence, asynchronous trajectory sequence that Roadrunner has. And we have our own custom methods in each of our subsystem classes. And then for our teleop is barely any lines because of how we have our subsystem set up. So all we have to do is follow the subsystem update methods when required, and that's how we kind of set up our code. So a subsystem is something like a wobble goal or a mechanism drivetrain or a turret, just to give some references. And you could also automate things like auto ejection. So with the fourth ring, instead of ejecting it here, you could reverse the intake. You could also automate things like the wobble goal drop off. So in a remote setting, you could take the shortest path possible to drop off the wobble. That's something that's cool. You could use a camera to detect the rings on the field. So a lot of people obviously had vision, but something you could also do is detect the ring on the field for bounce backs. The way you can do this is by using, just like an interpolation table. Another cool way that I discussed with Arnav, he was an alumni of 8719 Quantum Leap. What me and him discussed was using a 3D model, like a 3D view of the whole field and camera, and converting like a ring's position in the camera frame to a 3D distance from our robot. So you can do that based on the camera's height off the ground, the angle, and then where the rings read. And you can account for something like the ring size using angle offsets instead of like a direct measurement of like the width or height, so it scales appropriately. But just generally, it's really fun discussing these things, and if you have enough time and good software automation, it really helps with things like your autonomous program. Because a lot of teams were able to reach their max auto this year because of the way they implemented a lot of the software needed. That's like a very basic overview of our software. We have some other tutorials on the channel for our auto aim, so if you guys want to check that out, if it's useful for next season maybe, but apart from that, that's pretty much it for this video.